Hey guys, today we're going to go over infinite limits. So that's what this video will review, and then the first textbook set of assignments reviews infinite limits as well. So let's get started. All right, so the definition is a limit in which f of x increases or decreases without bound as x approaches c is an infinite limit. All right, so what we're talking about here really are vertical asymptotes. We're having our x value approach some c value, so some value on our x-axis, and what our function is doing is it's either going up to positive infinity or it's going down to negative infinity. So with these, we're really going to have to take a look at one-sided limits, because oftentimes we're going to have those opposing directions, right? And when we have that situation, then we're kind of stuck. In that situation, we have to default back a little bit, and it just does not exist because my limit from my left doesn't equal the limit from the right. So we have some properties of infinite limits that help us analyze things a bit. All right, so we're gonna let the limit as x goes to c of f of x equal infinity, and the limit as x approaches c of g of x is going to equal some constant value, some value L. So first we have the sum and difference property. And that just says that the limit as x approaches that c value of f of x plus g of x is just going to equal infinity. Because if I'm adding something so minuscule to infinity, it doesn't even matter, right? Or if I subtract something, sorry, make this a plus or minus. If I subtract something so minuscule, if I have positive infinity, right, and I add 3 to it, I mean, whatever. It's like being a billionaire and someone giving you 5 cents. You're like, oh, that's a cool little coin to play with. But they're not really going to add it to their wealth. That doesn't really mean much to them at that point. So they would still be considered a billionaire. It's not going to change anything. The next one we have is our product property. And that just says that if I take the limit as x approaches c of f of x multiplied by g of x, I'm also going to, I'm going to get infinity out. Hold on. I'm going to get infinity out when L is greater than 0, and I'll get negative infinity out if L is less than 0. So if that limit f of x is going to positive infinity, and I multiply that by a -4, I'm still going to get infinity out, but now that negation is going to make it a negative infinity. And then if I multiply f of x by like 10, I'm still getting infinity out because the limit as x approaches f of x is infinity, and it'll still just be positive. The final one is my quotient property. And that one states that the limit as x approaches c of g of x over f of x. So I want you to think about this one for a little bit. What we have going on here is we're approaching some c value. My g of x is staying constant. Let's just say it's 10. My denominator is going to infinity, so it's getting insanely large. So ultimately I have 10 over like a billion, 10 over a trillion, 10 over some insanely large number. That value is always going to be approaching 0. So this is going to be 0. So anytime you have a denominator that's approaching an insanely large number and your numerator is staying some constant value, your limit is going to be approaching 0. And that's a horizontal asymptote at 0 in those situations. All right. Let's also just look at, I just want to relate this to rational functions. So let's say we have the limit as x approaches 3 of 1 over x subtract 3. So if I were to graph this function, I would see that I have an asymptote at 3 because nothing got canceled out, right? It's all just the same. So I have an asymptote at 3. And then my function would look like this. And so as I approach 3 from the left, my function is unbounded. I'm going towards negative infinity. As I approach 3 from the right, I'm going to go towards positive infinity. So if we were to break this limit down to see if it exists algebraically, we would need to say the limit as x approaches 3 from the left is negative infinity, because as I'm coming from the left here, I'm going down to negative infinity. The limit as x approaches 3 from the right of 1 over x subtract 3 is a positive infinity. Since these two do not match, we would say that this limit does not exist. So what you'll see in your homework is oftentimes it's either going to ask you from the left or from the right, not this whole piece. However, there are instances where that whole piece is going to go to infinity. Let's take, for example, we have the limit as x goes to 3 of 1 over x minus 3 all squared. So that function, conversely, and I'll show you how to analyze that kind of with both scenarios, is going to look something like this. And so notice the limit from the left and the limit from the right are both approaching positive infinity. So this one would just be positive infinity. And again, you can put that DNE in parentheses if it makes you feel better. But since they're both going in the same direction, we would say that that's approaching positive infinity. The reason for that is because if I put in like 2.99999999999, I'm getting an insanely small number, right? And then I'm squaring that insanely small number, which is making it even smaller, and it's also making it positive. If I put in 3.00000000001, I again have an insanely small number. I'm squaring it, so I'm doing 1 divided by this really, really small number, which makes my whole fraction really large. So if you're not believing that like theoretical concept there, grab a calculator and do like 1 divided by 0.000000001, and you'll get a very large number back out. So anytime you divide by a really small number, you get a really large number. And anytime, like we just previously saw, when you have 1 over an insanely large number, like infinity, or a number close to infinity, you're going to get 0 out because that value is approaching 0. The other thing I just want to look at are limits to infinity and beyond. So let's say that we had, and this really depends a lot on your recall of rational functions. So let's say we have the limit as x goes to positive infinity of 2x over 3x plus 4. Remember when we were graphing rational functions? If we were graphing this rational function, because these degrees match, we had a horizontal asymptote at y equals 2/3, right? Whatever this ratio was. So we knew that whatever this function looked like, I'm not quite sure, I would need to graph it. I would assume it looks -4/3 is it would look something like this and like this, I would assume. That as I go to positive infinity, it's approaching 2/3. So this would be 2/3. The calc explanation behind that is that, again, when you add something like +4 to something that's going to infinity, this is negligible, right? That's just like blah, it's gone. So what we have now is 2x over 3x. And this numerator is getting large at the same rate that this denominator is getting large. So it's like they're being able to be canceled out and you're just being left with 2/3 because the rate at which these are increasing is the exact same. Conversely, if we had the limit as x goes to infinity of 3x squared plus 4 all over 5x, notice now my numerator is getting larger at a much, much faster rate than my denominator is. And I'm only looking at these leading terms. So if I look at these leading terms, I see that this numerator, right, is going to infinity at a much faster rate than this denominator is. So we would say that this one's going to positive infinity. The last situation that can occur with these is if my denominator, similar to what we saw before with the function, I'll just do x minus 1, my denominator is getting larger faster. So I have 1 over an insanely large number. And remember, when I have 1 over an insanely large number, I get 0 out. So, and this relates back to like 1 over x minus 1. Remember, if the degree on top was less than the degree in the bottom, then we had a horizontal asymptote at 0. So that matches pretty perfectly with those rules and properties that we had last year, right? And then this oftentimes is a situation where maybe these cancel out. This case, we're not canceling. We do have a vertical asymptote at 0. But you would have an oblique asymptote, right? So we would go ahead and we would divide that, and we would have a function going towards positive infinity, like we saw last year. So try to default to your rational functions when we're dealing with these limits. All right, email me if you have any questions. I think this will, most of the homework is on that first part. There may only be a few sections on this. Enjoy.